Okay, the discussion continues on carbon dating. The percentage of carbon-14 was expressed as an exponential function, just to remind you. Before we were writing that the amount of radiation or carbon radiation in something was originally 100%, but it was multiplied by 1/2 to the power of the time that the thing had been dead divided by 5,730 years. Since a log function is the inverse of an exponential function, it's possible to switch the variables and write the age as a logarithmic function to the percentage of carbon-14. The table below shows data for 5 recently discovered fossils. So these are fossils where somehow we got their age by some other means, and then we checked their carbon percentages, and this is what we came up with. So as time passes, the amount of carbon drops rapidly at first and then more slowly. Create a scatter plot on a graphing calculator. To confirm that a logarithmic function is an appropriate model for the data. Okay, well, to get a scatter plot, let's clear this old stuff out of here. You go to Stat, and then it's already on Edit. It assumes that's what you want, so just hit Enter once. And now it's ready to take data. So we're going to say the percent of carbon-14 is our first variable, and it goes 95, 79, 68, 38, 27. And the ages that go with that are 425, 1,950, 3,191, 8,000, and 10,824. Okay, if we graph those, to graph those you have to go second y equals, and here's your first plot. It says, I'm going to use list 1 and list 2. That's exactly what we want, but right now it's off. If you select that plot and then hit Enter to turn it on, now you can graph it, and we don't see anything because my window's out of whack. Sorry. We want our numbers to go from 0 to 100, essentially. And for our number of years, we need to get to at least 10,000. I'm going to go to 20,000. We'll see what that does for us. So 0 to 100% carbon, carbon radiation, and age in years. Graph that. There we go. So it's dropping, and it drops more slowly as time goes on. Could that be a logarithm? Yeah, it's curving the wrong way. There must be a negative number in it someplace. But it could have a vertical asymptote up here, and then it drops quickly, drops more slowly, and it looks like it's eventually going to hit a vertical, or an x-intercept. So yes, that could be a logarithmic function. Now, use the logarithmic regression feature of the calculator to determine a function in the form y equals a plus b natural log x, which models the data. Okay. So, doing a regression. We've already got our data in. We didn't necessarily have to graph it, although we usually do. But now that we have that graph, we can go to Stat. We want the Calc menu, so just use the right arrow to go one step over to the right. And you've got all these things here that say reg. These are all different kinds of regression. So we have linear regression, quadratic regression, cubic regression, quartic regression, a different kind of linear regression, and here is logarithmic regression. Hit Enter for that. There's things you can tweak about the way this is calculated, which we don't need to tweak right now. So it's saying natural log regression. Do you have anything else to tell me? If the answer is no, just hit Enter. It thinks, and it says, your equation is a plus b natural log x. By a, I mean 38,000, and by b, I mean 8,265.8. So, let's see what we get from that. 38,067. We get y equals 38,067. And then our b was minus 8,266. 8,266 natural log x. It said integer values, so I didn't carry any of the decimal points. I just rounded each of these to the nearest whole number. Now, on a graphing calculator, display a graph of the regression equation over the scatter plot, and let's see if they match. So, 38,067 minus 8,266 natural log x, close your parentheses, and if we're lucky, it'll go right through those points. Look at that. So our regression worked. This equation is doing an excellent job of predicting where those points ought to be. So, part C, roaring success. Part D, use the graph in C to answer the following questions. A bone fragment in the shape of a mammoth with the image of a mammoth was discovered in Florida. If the carbon dating test indicated 20.3% carbon, estimate the age. So, if the percentage left was 20.3, we can put in that value and say, okay, if we're at 20.3% carbon, how old is this thing? Answer, same thing we got in the previous example, 13,000 years, give or take. And now working backwards, if a skeleton is about 10,000 years old, what percentage should we get if we analyze its carbon content? Well, we can put 10,000 in here. There it is. And then again, we use intersect to find where those cross. So remember, second trace, pick intersect, enter, enter, enter. And it says, if it's 10,000 years old, it'll have 29.8% of its carbon left. 29.8%. Same answers that we got from the previous example. It's just in the original example, we had years versus carbon percentage, and our graph was going like that. In the new version, we have carbon percentage versus years, and, well, the graph still looks like this, except now it's like, if you have 100% of your carbon, then you are very young. If you have 50% of your carbon, then you are old. If you have like 10% of your carbon, then you are very old, or you've been dead for a very long time. So it's the same information, it's just we started out using one kind of function, and now we're working with an inverse function. Or more precisely, we started out using an exponential, 1/2 to the power of a number, and now we're using a logarithm to do the same job. They're inverses, but they're talking about the same data points. It's just here they're years, comma, percent, and in the inverse they're percent, comma, years, because the x and y have traded places.